propiedad. Les recordamos no obstruir.
Tarde. Muchas gracias por acompañarnos. La Universidad Nacional Autónoma de México les da la más cordial bienvenida a la conferencia Quantum Science with Giant Atoms con el doctor Serge Haroche, Premio Nobel de Física 2012. Agradecemos la presencia de las autoridades que hoy nos acompañan.
Buenas tardes. Hola a todas las personas que seguro están como nosotros aquí en Universum, el Museo de las Ciencias de la UNAM, tan emocionados por recibir esta visita tan especial. Premio Nobel de Física 2012, el doctor Serge Haroche, pero para presentarle voy a pedirle al doctor Alfred Uren del Instituto de Ciencias Nucleares de la UNAM que me acompañe en el escenario y él les va a leer un poco acerca del trabajo y bueno, pues les va a contar un poco acerca de quién es nuestro ponente magistral el día de hoy. Alfred, por favor, bienvenido y muchísimas gracias a todos por venir a Universum el día de hoy.
Good afternoon. It is my distinct pleasure to introduce Professor Serge Haroche, who will deliver a plenary talk. I will read a little bit about his trajectory. Professor Serge Haroche was born in 1944 in Casablanca. He graduated from École Normale Supérieure, ENS, receiving his doctorate from Paris 6 University in 1971. After a postdoctoral visit to Stanford University, he became full professor at Paris 6 University in 1975, a position he held until 2001, when he was appointed professor at Collège de France in the chair of quantum physics. He has been part-time professor at Yale University from 1984 through 1993, member of the Institut Universitaire de France, 1991 through 2000, and chairman of the ENS Department of Physics from 1994 through 2000. In September 2012, he was appointed administrator the Collège de France, equivalent to president of this institution, a position he held until September 2015. Since then, he has been professor emeritus at Collège de France. He has received many prizes and awards, culminating in the 2012 Nobel Prize in Physics, shared with David Wineland. Professor Haroche's research has mostly taken place in the laboratory Kastler-Brossel at ENS. His main research activities have been in quantum optics and atomic physics. He has made important contributions to cavity quantum electrodynamics, cavity QED, the domain of quantum optics, which studies the behavior of atoms interacting strongly with a field confined in a high Q cavity, a box made of highly reflecting mirrors. An atom-photon system isolated from the outside world by metallic walls realizes a quintessential model of quantum optics, which Serge Haroche has used to test fundamental aspects of quantum physics, such as state superposition, entanglement, complementarity, and decoherence. Some of these experiments are actual realizations in the laboratory of the thought experiments imagined by the founding fathers of quantum mechanics. We can mention the observation of single atom spontaneous emission enhancement in a cavity in 1983, the direct monitoring of the decoherence of mesoscopic superpositions of states, so-called Schrödinger cat states, in 1996, and the quantum non-demolition counting of photons in 2007. By manipulating atoms and photons in high Q cavities, he has also demonstrated elementary steps of quantum information procedures, such as the generation of atom-atom and atom-photon entanglement in 1997, and the operation of quantum logic gates involving photons and atoms as quantum bits in 1999. The work of Haroche and Wineland has given a big push to quantum information science. Teaching and science dissemination have been an important part of his activities. We had the fortune to listen to his lectures at the Latin American School of Physics in several occasions at the Colegio Nacional. The invaluable material of his book, Exploring the Quantum Atoms, Cavities, and Photons, is based on the lectures on quantum information he gave at Collège de France from 2001 to 2006, and at École Normale Supérieure from 2003 to 2006. Most of atom cavity experiments, which are at the heart of the book discussions, were carried out by the research team at ENS. This book appeared exactly at the time when the laboratory got an exceptionally good cavity, which finally made possible the experiments we had been dreaming about over the previous 15 years. And in the months and years which followed, they were able to observe many of the effects they had predicted in theoretical papers and announced in that book. In another recent book that has been translated to Spanish with the intriguing title La Luz Revelada, Professor Haroche gives a literal enlightening account of what we know about light today, how we learned about it, and how that knowledge has led to countless inventions that have revolutionized daily life. Today, he will be talking to us about his pioneering research on Rydberg states, the preparation of these atoms of gigantic dimensions in the atomic scale and their control dynamics by the influence of photons yield a matter-light system with amusing properties that have been at the core of several of the many important contributions of the group he has led. It is for us a great privilege to listen to him describing his work. Thank you, Professor Haroche.
So, thank you very much for this very kind introduction. I must first apologize for not being able to speak in Spanish, and also for what is written at the bottom of this slide here. In fact, I will be going next week to New York to give a talk, and it will be the same title, but here you have the privilege to have a preview of my talks of next week. I want to say that I'm very pleased to be here. I remember I have been many times in Mexico and attending some schools of South American schools in quantum optics, in which I had the privilege to present some of the results I'll be talking to you about today. And but I think the last time I came here was around the years 2005, 2006. So I don't think I was able to present the experiments that I will be talking to you about. What I want to discuss today is the physics, what I call the physics of giant atoms. And as has been kindly introduced, these giant atoms are called, in fact, Rydberg atoms, from the name of the Swedish physicist who was the first to give a formula giving the spectrum of these very excited atoms. So what I will be talking about is first about the history. These atoms have played a very important role in the history of quantum physics. Because, in fact, Niels Bohr, when he made the first model of the hydrogen atom, in fact, described Rydberg atoms, and he introduced for the first time Planck's constant in the context of atomic physics. So it was really very important on the theoretical level. But these atoms, their properties were known, but it was very difficult to study them in the lab because they are very fragile, and one had to wait until the advent of lasers to do it. And when the lasers came, a lot of groups started to be interested in these atoms. And my group in Paris did the experiment, which have been kindly introduced and which I'll be talking about. Then the next step, starting in the year 2000, when going on up to today, these atoms have become also very important in quantum information science because they interact very strongly with each other, and they are ideal devices, ideal system to implement a lot of experiments in the domain of quantum information, quantum simulations. So this is an introduction which justifies this outline. I will first describe briefly how Rydberg atoms have been important in the birth of quantum physics. Then in the second part, I will talk about circular Rydberg atoms in cavity quantum electrodynamics. And I will show how these experiments allowed us to illustrate the basic features of quantum physics, state superposition and entanglement. And then the third part of the talk, I will discuss more recent work about circular Rydberg atoms for quantum information. So let's start with the beginning. The story started, in fact, a long time ago. It has been known since the beginning of the 19th century that atoms absorbed and emitted light on discrete frequencies, sharp lines, not a continuum of light. This was known since Fraunhofer at the beginning of the 19th century, but nobody had an explanation for that. You see here what is called the Balmer series of hydrogen, and you see on here the red line, then you have a blue line, a light blue line, a dark blue line, and a violet line. And the position of this line, making a discrete spectrum, are associated to couples of integer numbers M1 and M2. You see here with from Rydberg handwriting, the formula which expresses the position of these frequencies. It's a difference of two terms, 1 over M1 squared minus 1 over M2 squared. And this defines the Balmer line if you take for M1 the value equal to 2. You see, for example, that the red line corresponds to M1 equal 2, M2 equals 3. The blue line, M2 is equal to 4. The deep blue line, M2 is equal to 5. And the violet line, M2 is equal to 6. If you change M2, the M1 value from 2 to 1, you get the Lyman series. If you take M1 equals 3, you get another series. And Rydberg also found that if you want to find out what are the position of the lines in alkali atoms, which are a little bit different from hydrogen, the only thing you have to do is to add a correction to M1 and M2, adding a quantity C1 and C2 to this term, which is defining the spectrum for, let's say, for sodium or lithium or cesium. But this was rather mysterious. Nobody understood really where was this coming from. And it took about 25 years from Rydberg formula until Bohr unveiled a part of the mystery. But in order to get there, we need to have a look at what happened at the end of the 19th century and until the year 1913. And I say this is the beginning of quantum physics, and this is the understanding that the world was not continuous. According to classical physics, all physical quantities could be represented by continuously varying numbers. And quantum physics introduced the fundamental graininess, the fact that if energies and angular momentum and other quantities could take only discrete values. This happened, of course, with the work of Max Planck and Einstein between 1900 and 1905. Planck, to make sense of the spectrum of black body radiation, of the fact that when you heat a piece of matter, it emits light, to understand the spectrum of this light, which was impossible to understand with classical theories, with Maxwell's equation and thermodynamics, made the hypothesis that light exchange energy with matter by discrete packets of energy, light of frequency f, corresponding to a packet of energy E equal hf, where h is the famous Planck's constant. And I just remind you here that, of course, h has a dimension of an energy multiplied by time, which is also a momentum multiplied by length, that is an angular momentum. It's a very, very tiny quantity. All phenomena occurring at the macroscopic scale involve huge number of quantities which are expressed in a very large numbers when you measure them by the Planck action. And that was rather mysterious. Einstein went one step further. He said it's not only the exchange of energy between matter and light, which are quantized. Light itself is made of particles, which will much later on called photons. And of course, in this talk, photons will play a very important role. And so this was the first very important thing, which introduced graininess in light. But at the same time, other experiments, other facts presented the fact that matter also was grainy. In 1897, Thomson discovered the elementary charge, electronic charge, the electron. And a few years later, in 1909, Rutherford discovered the positive charge nuclei. So this was a big breakthrough, which shows that matter also was made of discrete quantities, was not continuous. And very soon, the planetary model of the atom emerged. Atoms were made of a positive charge around which electrons were rotating like a small planetary system. This was in particular advocated by Jean Perrin, who got a Nobel Prize for measuring the Avogadro number back in the 1920s. So the stage was ready for the big breakthrough, which happened in 1913 with Niels Bohr's work. In fact, what Bohr started with the simple model of a positive nucleus with an electron going around, which is the simplest of all atoms, hydrogen. And he chose to discuss the simplest possible orbits, which are the circular orbits. And what he said is something very simple. He realized that Planck's constant had the dimension of an angular momentum. So he said, in fact, the electron angular momentum is quantized, and it can take only values which are multiple integral values of Planck's constant. In fact, what he used is not exactly Planck's constant h, but it used what is called the reduced Planck's constant h bar, which is h over 2 pi. And we will understand why he had to do that in a moment. But the important point is that an angular momentum, which is, in the case of the electron motion, it is just the radius of the orbit times the velocity on the orbit multiplied by the mass, which is a quantity which describes the amount of rotations that you have in the system, is a multiple of h bar. So it gives one relation between the velocity and the orbit radius. You have another relation which is obvious, which is just Newton's law, which expresses the fact that the Coulomb force, which is E squared over R squared, is equal to the acceleration mv squared over r of the electron in the orbit. So it's another relation between r and v. And when you solve this couple of equations, which is just a high school problem, you find very immediately that the radius is proportional to n squared. And this is a formula which gives the radius on the orbit. And you see that the ground state, which corresponds to n equal 1, has a radius which, with the constant that you see here, is about half an angstrom. And the next orbit is 4 times larger, the next one 9 times larger, and so on. So the quantization comes immediately. But not only the quantization of the radius, you also quantize the velocity, which scales as 1 over n. And this is also something which comes directly from this equation. And the energy, the binding energy, which is inversely proportional to the distance to the center, scales as 1 over n squared. So this came directly from this very simple hypothesis. The next step that Bohr took was to say that, in fact, the atom could emit or absorb light only when the electron jumped from one orbit to the other, and that due to the conservation of energy, it happened by emitting or absorbing a photon whose energy hf was equal to the difference of energies. And this gave immediately the famous Rydberg formula. So the Rydberg formula comes from this simple observation. And in fact, just to make it coincide to the experimental values, he understood that h has to be replaced by h over 2 pi. That's the only kind of adjustment that he made. So you see immediately from this kind of reasoning that these circular Rydberg atoms played an essential role in the birth of quantum physics. but there was still some questions. And another idea that Bohr had was a relationship between classical and quantum physics. And this is also something which comes from looking at these Rydberg states. What the correspondence principle, which was enunciated by Bohr at that time, expressed the fact that when you increase the quantum, when you get to larger and larger quantum numbers, the system becomes larger and larger, and you should merge quantum physics into classical physics. It's called, and this also helped Bohr to find this equation. And the circular Rydberg atom is an excellent example of that. If you take for n, if you take for n a value equal to, let's say, 100, the size of the orbit becomes the order of a bacteria, which is a micron size. So it's still small. But if you think now of n equal 1,000, you get to the size of an atomic, the diameter of an atomic hair, 1/10 of a millimeter, which is already something macroscopic. And if you dream about a Rydberg atom, which would have n equal to 10,000, it would have the size of a pea or a cherry. So you really go by just increasing the quantum number from the microscopic to the macroscopic scale. Of course, it's difficult to make and study very large atoms, as I will see in a moment. And the correspondence principle is also obvious if you look at the frequencies that the atom emit. When n is large, the atom will, by going from one state to the next, emit a frequency proportional to 1 over n squared minus 1 over n plus 1 squared. And this is approximately 1 over n cubed. So you see that, in fact, the period of the electron around the circle is, if you square this period, you find something varying like n to 6 power, which is the cube of the radius. And this is nothing but the third Kepler's law. You find with these large quantum numbers, the property which is known for the orbit of the planets, that the square of the period is proportional to the cube of the radius of the orbit. And you see the proportionality constant appearing here. So this was very interesting, but still Einstein was not very happy about that. He said that this quantization, Bohr's quantization, looked artificial. Why do you have to quantize the angular momentum and not something else? And in a famous letter he sent to Lorentz in 1920, he said, these Bohr's rules are the worst of our quantum puzzles. And the puzzle was resolved a couple of years later by Louis de Broglie in 1923. Louis de Broglie generalized this wave-particle dualism that Planck and Einstein had introduced for light by saying that if light is at the same time matter and wave, then electrons, which are supposed classically to be particles, have also a wave-like character. And so he generalized to matter the photon properties. The photon, which has an energy hf, has a momentum hf over c, which is h over lambda. And so what he did is just to admit the same relationship between wavelengths and momentum for the massless photon to a massive electron. And he said to the electron, you should attribute a wave, you should make a wave, correspond a wave whose wavelength would be h over mv, where v is the velocity of the electron. And he predicted that you should have interference effects related to matter waves. But in fact, this was applied first to the Rydberg, circular Rydberg atom. If you look at this formula, what it means exactly, mvr is equal to nh bar is equivalent to saying that n lambda is equal to 2 pi r. That is, you need to have an integer number of de Broglie wavelengths on the circle. And this is a resonance condition. So matter waves obey the same kind of resonance condition you have in acoustics. If you take, for example, a violin string, it has an integer number of wavelengths between the two endpoints, and you can change the frequency by just moving one point. This is what the violinists are doing. And so he introduced a kind of musical harmony in science, in physics, related to Planck's constant. And in fact, it's interesting to realize that all this started by consideration about circular Rydberg atoms. But of course, from there on this was exactly 100 years ago, the birth of quantum physics. The following year, as you know, Schrödinger discovered the equation which describes the propagation of these waves, and this was the beginning of quantum physics with all the successes it had in the future. And then people forgot about circular Rydberg atoms for about half a century because they were impossible to produce in the lab. But what are let's just summarize on this slide the properties of this atom. And I compare here the properties of low excited atom when n takes a value 1, 2, 3. With what happens, let's say for Rydberg atom with n equal to 100. The first thing that I discussed already is the fact that the orbital size increases n squared. That is, instead of having a diameter of the order of 1 angstrom, now we have diameters of the order of 1 micrometer, which is 1,000 times bigger. The radiative lifetime, these atoms which are accelerated, an electron accelerated around the nucleus, lose energy and radiate electromagnetic waves, as Maxwell's equation predicted. For low excited state, the lifetime is of the order of 1 nanosecond. If you go to highly excited state with n equal 100, you have two kinds of states. If the state has a low angular momentum means that the orbit is elliptical with the electron passing very close to the nucleus at one part of the orbit. Then the lifetime is about 100 microseconds. So it's much longer than the ground state, but it stays short. If you go to the circular state, since the electron is always as far as possible from the nucleus for a given energy, the acceleration is very small and the radiation rate is much smaller, about 1 second for the circular state. So they become practically stable states, and that's why they're called Rydberg atoms. It's not, these are atoms that you can study in the lab and keep them for a rather long time. And we see that you can do even much longer times. Another property is the spacing between the levels, which define the wavelengths with which the atom will interact. For low excited state, it's scaled as n-3. For low excited state, the frequencies are in the range of 10 to the 14 hertz. That is optical frequencies. It explains why atoms emit and absorb light. But for Rydberg states, it falls in the microwave domain. And these atoms are very strongly coupled to microwaves, which is an important feature. The last property I would like to discuss is the interaction of the atom between themselves. If you have two atoms and you look at their interaction, you have the famous van der Waals force. Each atom has a fluctuating dipole, which induces the dipole on the other atom. The two atoms are coupled by these dipoles, and a force is exerted between them. This force scales as the 11th power of the principal quantum number. Why? Because each dipole is n squared, so the product of dipoles is n to the 4th, and the van der Waals interaction is a second-order interaction. So it's n to the 8th divided by the energy spacing, second-order perturbation theory, which is another n cubed. So it's a huge force, it's a huge interaction. For ground state atoms, they have to be at 1 nanometer distance, a molecular distance, to see this force, which would give rise to 100 megahertz shift. For Rydberg atom at 10 micrometer or 20 micrometer distance, they experience the same interaction. So you can have them interact at macroscopic distances, and this will be very important in the last part of my talk. But as I said, observing these atoms in the lab is very difficult because the other side of the medal is that if they are very have strange properties, these properties are very fragile, and anything will perturb collision with other atoms, black body radiation, stray electric and magnetic field. So you have to protect them. And for 50 years, nothing happened. In fact, the only place where you could see these atoms was in the interstellar medium. Radio telescopes detected radio frequency lines which were attributed to these atoms. So what happens at the interstellar space, the light from stars is photoionizing atoms. So you have positive ions and negative electrons, and the electrons are captured on circular orbits at a large distance from the positive core, and then they cascade down by emitting microwaves. And you see here lines corresponding to delta n equal 2 transition in hydrogen from 137 to 135. You see the same line for helium. You see this isotopic, this shift between hydrogen and helium is due to the relative mass effect. In fact, I assume that with all what I said so far, that the core has an infinite mass. In fact, it does not have an infinite mass, and in fact, the core and the electron are rotating around each other, and this wobbling introduces small change in the effective mass that you have to take into account, and which explains these shifts. And you see again here also the shift between helium and carbon. This is the main line, hydrogen 109 to 108. And you see these are big atoms, but the record, which has been measured about in the 1960s already, is a line in carbon corresponding to the transition between 732 and n equals 732 and n equals 731, which correspond to an atom which has a radius of 53 micrometer, which is really a very big atom. But then one had to wait another 10 years until the lasers were able to excite these atoms from the ground state. And this was the beginning of Rydberg atom physics back in the 1970s. And it is about the time when I joined the group of people who in the world start to be interested into these atoms. You see here the spectrum of the energy spectrum, the energy scale of rubidium. You have here the ground state, the first excited state, and then the series of Rydberg states converging towards the ionization limit. And the first way to excite them was to make a stepwise process. A first laser excite from 5s to 5p, and then you use another laser at a shorter wavelength to get as close as you can from the ionization. So you need lasers which have a very sharp line to be able to distinguish between these states. And when you do that, what you reach with these lasers are low angular momentum states. Why? Because each photon carries 1 unit of angular momentum, and so conservation of angular momentum makes it such that you can only excite S, what is L equals 0 state, which are S state, or L equals 1 state, which are P state, and so on. And the transition between these states falls in the microwave domain. So in fact, what you are exciting are Rydberg states of low angular momentum state, which classically are elliptical orbits. But you can feed angular momentum into these atoms by having them absorbing radio frequency photon of circularly polarized light. And then you can reach, in the end, the famous circular atom. I will say more about this process later on. In fact, it has been pioneered by Dan Kleppner at MIT. The way you prepare circular state from the ground state in 2 steps. First, you feed energy to get at high energy levels, and then you feed angular momentum with low energy circularly polarized photons. And so this was the beginning of this long story. How do you detect them? One very popular way of detecting them is state selective detection by field ionization. So you can let this atom pass between 2 metallic plates and apply an electric field. And this electric field will pull in opposite direction the circular orbit of the electron and the nucleus. So it's like trying to close an umbrella. You get the tip of the umbrella further and further away from the rim. When you do that, you can very easily find that the frequency of the circular transition is slightly changed. This is called the Stark effect. You just slightly change the distance between energy levels by applying an electric field. And this is the method we employ to tune the frequency of the Rydberg transition in and out of resonance with a cavity, for instance. But if you keep increasing the electric field, what happens is that you pop more and more the ion out of the plane orbit. And at some point, the electric field is big enough so that the atom breaks and you eject an electron in one sense, the ion in the opposite direction. What is very interesting is that this breaking occurs at different electric field for different excited states. The more excited is the state, the smaller is the field which is required to break the atom. So in fact, what we do is we apply a ramp of electric field, and in increasing electric fields, you ionize first the most excited state here, n equals 60, and then n equals 51 in a larger field, 58 in a larger field, and so on. And you see that you can detect selectively in the ramp the different Rydberg states. And it means that if you make a transition using, for example, microwave from n to n-1, you will detect it by the change in the electric signals that you get in this ramp of electric field. So this is a method that we use for many years, state selective ionization in a ramp of electric field. This method is destructive. Once you have observed it, you have to sell another atom and start again. Later on, I will tell you about the non-destructive detection of Rydberg atoms. So this brings me to the second part of my talk, which is how we did use these atoms to realize textbook experiments to test the quantum postulates. And you see that typically what we do is that we send a circular Rydberg atom across a cavity, which is made of two mirrors facing each other. And we study the interaction of the atom with the cavity field. What is very interesting with Rydberg atoms and with this kind of experiments that you can compute all the orders of magnitude without knowing any quantum physics. It's just classical physics, back of the envelope calculation. Planck's constant enter into play. That's true, but you can calculate everything from there on. Let's look at something very simple. We were studying the transition between n equal 51 and n equal 50, which occurs around 50 gigahertz, which is a wavelength of about 6 millimeters. So the mirrors were a few centimeters apart to sustain this mode. The first important parameter is the vacuum fluctuation of the electric field in the cavity. Quantum physics tells us that you cannot have zero field in the cavity. Because of Heisenberg uncertainty relation, you have fluctuation of the electric field, and this fluctuation corresponds to half a quantum, which is the ground state of the field oscillator. So what you have to do typically is to take the energy of one photon and divide it by the cavity volume and epsilon naught to get something which is homogeneous to an energy. And you find a field vacuum of about 3 millivolts per meter. And this is just related to the volume of the cavity, which you just measure with a ruler cavity. You put Planck's constant in the game and you find this. Now, this is a field with which the atom interact. And what is the interaction? Just the product of the electric dipole of the atom with this famous n square factor times the field vacuum. When you compute this and divide by h bar, you get a frequency, which is 50 kilohertz, 2 pi times 50 kilohertz. So this is the order of magnitude of the coupling between the atom and the cavity field. It means that it will take a time which is of the order of 1 over 50 kilohertz, that is a few microseconds to get the coupling active. Another important order of magnitude, the ratio between the frequency of the photon and the coupling, this ratio is 1 part in 10 to the 6. So you see that the coupling is rather weak. The energy change produced by the coupling is 1 part in a million of the energy of a single photon. So it's a very small coupling, but it has a very important effect. To do that, you just have to look at a very, very simple picture, which is the energy scale of the atom field system. The ground state of the system is what is important here is that you will couple two nearby Rydberg levels. I call G the state with n equal 50 and E the state with n equal 51. What is the ground state of the system? Obviously, you need to put the atom in the lower state and 0 photon. So this is the ground state. Now, when you put one excitation in the system, you can do it in two different ways. Either you excite the atom in vacuum, E0, or you add 1 photon and have the atom in the ground state. The state E0 and G1 have the same energy, provided the atom is exactly in resonance with the cavity field. And you achieve this resonance by playing with the electric field, which tune very finely the atom in resonance with the cavity. Now, this is the most basic problem in quantum physics. When two systems have the same energy and they are coupled together, you have a splitting which occurs, and you have a positive superposition E0 plus G1, which is shifted upwards, and the negative superposition E0 minus G1, which is shifted down, and the distance between these two states is precisely equal to the coupling. And this gives rise to a very simple phenomenon, which is a basic phenomenon in quantum physics, which is called the vacuum Rabi oscillation. it's a quantum interference effect. Suppose that you prepare the atom in the excited state and send it in the empty cavity. This state is no longer an eigenstate of the system. E0 is a superposition of these two states. So this state will evolve in time at this frequency. And if you measure at a later time the probability to find it in the other level, what you are doing is something which looks like a Young double slit experiment. You start the system in one state, the system evolved in superposition of two states, and you measure the probability to find it in the state or the other one. And in fact, this is a quantum interference experiment, which is called the Rabi oscillation, which shows that, in fact, the probability to find the atom in E or in G oscillate in phase opposition. And how do you see that? You just let the system evolve for a given time, then you freeze it by getting the atom out of resonance suddenly, and you measure either you find the atom in E or in G. You do it a large number of many times to measure a probability, then you change the delay and you reconstruct this curve. So it's very simple, and this is what we have done, and I will discuss it here. We have two kinds of experiments. The first experiment we did was with a cavity like that, the atom going across the cavity one by one. And so they interact during their the time they cross the cavity, which takes about 100 microseconds at the velocity of atomic beam, which is a few hundred meters per second. So this was the first experiment. Then we improved the setup by using cold atoms. What we do is that we put now the cavity horizontal like that. Here we have what is called the magneto-optical trap, in which cold atoms are cooled to a very low temperature. And then we send a pulse of light upwards, which eject the atoms from this cold cloud, and the atom go up and they cross the cavity with a very small velocity. And just before they enter in the cavity, you prepare them in the circular state. And with this second setup, we have an interaction time of milliseconds, much longer. And you see the difference here. This was the first Rabi oscillation that we got. And you see here that we can see tens of Rabi oscillations. So why is it interesting? First of all, what happens here, this quantum interference experiment, in fact, the system is evolving in a superposition of E0 and G1 with amplitudes which are the cosine and the sine of this famous Rabi frequency. So you see that in general, the system is in a superposition of two states. In fact, what you get is, of course, entanglement between the atom and the photon field. You see, in general, this kind of superposition cannot be written as a product of an atomic state by a field state. It's a superposition, which means that if you measure the atom and find one result, you will know what is the state of the field. And this is typically what is done in the experiments of entanglement. You just prepare a system, let it interact, separate the system when the atoms leave the cavity. And when you make a measurement on one part of the system, it has an immediate effect on the probability to finding result on the other part. So there is a lot of literature which has been discussed about that, about entanglement. And I just remind you that the Nobel Prize in Physics last year was given to Aspe, Clauser, and Seilinger, who did this experiment with photons separated by large distances. Here, the separation is a few centimeters when the atom leaves the cavity, but the principle is the same. You see, for example, you start from E0. After half a Rabi oscillation, you get into G1, so you can prepare one photon deterministically. You know that you have one photon in the cavity. And if you stop just halfway here, you prepare E0 plus G1, which is a maximally entangled state. So why are these experiments interesting? When you entangle systems, it means that what you do on one system react on the other. This is typically what you do when you want to build a quantum gate. The atom, which is in state E or G, is like a quantum bit taking value 0 and 1, and the photon field 0 and 1 is also a qubit. And when you entangle them, it means that you couple them in a coherent quantum way. And so this is equivalent to preparing quantum gates. And so in this way, by just modifying a little bit the setup, we showed that it was possible to realize quantum gates in which a photon controls the state of an atom. Then if you send another atom after that, the first atom controls the state of the second one because they exchange a photon in between. So this was the first series of experiments. Another very kind of textbook result is what happens if you do the experiment not with 0 or 1 photon, but if you look at the radiation of an atom crossing a cavity which contains a coherent field. What is a coherent field? It's just a field which is produced by a classical source. So you inject in your cavity a small classical microwave field which has a well-defined phase. Now, what the Heisenberg uncertainty relation tells us is that if the field has a well-defined phase, it cannot have a well-defined photon number because there's an uncertainty between the energy and time, which is between the energy of the field and the phase of the field. And so what you have prepared, in fact, is a superposition of photon number state with a probability distribution pi of n. Each gives a radio oscillation at a frequency proportional to the square root of the number of photons. So what you are observing here is this formula, which shows that you have very fast a collapse of the radio oscillation, and then at a later time, a revival of the radio oscillation. This collapse and revival is a proof of the discrete nature of the photon field. Why? Because if you take the Fourier transform, of this radio oscillation, you see discrete peaks, which correspond to the probability to have discrete photon number into the field. And the distribution of the amplitude of these peaks gives you the Poisson distribution of the photon number in the field. If the field was a classical field without discreteness, here you would have a continuous curve and not a curve with maxima and minima. And moreover, if you plot the values of these different frequencies, you find the square root of n, you find that the radio oscillation in increasing photon numbers follows a parabolic curve corresponding to square root of n plus 1. So this experiment, you did that in 1996, and it was a real obvious proof that a small field, a microwave field in a cavity, is quantized in terms of photons. Then we did the famous experiment in which we measured a field without destroying it. So what we do in this experiment is, instead of looking at a radio oscillation, which involves exact resonance between the atom and the field, we slightly displace the frequency of the atom so that it cannot resonate with the field, and so the radio oscillation doesn't happen. But what happens is now that the state E and the state G are slightly displaced. This is called the light shift. This shift is proportional to the square of the coupling, inversely proportional to the detuning. So we take a detuning of a few hundred kilohertz, and we get a shift of about 3 kilohertz, a displacement which is produced by a single photon in the cavity. If you have n photons in the cavity, the shift becomes n times omega square over delta. So you see now that the frequency shift experienced by the atom is proportional to the photon number. So if you can measure this shift, you measure the photon number, but you don't destroy the photons because the system is non-resonant. So what do? We start with we just probe the vacuum field in the cavity. Since we are not at 0 temperature, which is impossible, there is always a small probability that 1 photon will occur. And at the temperature we're working it, the probability to have 1 photon in the cavity is 5%. So 95% of the time our cavity is empty, and 5% of the time there is 1 photon which pops in and out randomly. We call 1 the atom with n equal 51, 0 the atom with n equal 50, just because we want to give use the language of information theory. Each atom provides 1 bit of information. And what do? We probe the atoms by exciting the atom before and after they have crossed the cavity with a microwave field, which is resonant with the transition here. So this field has a frequency different from the field in the cavity. The field in the cavity just shifts the transitions, but the field that we apply here is a classical field. We just produce a transition. And you see what will happen in the simplest situation is that if the atom is prepared in state 0, it will jump to state 1 only if and only if there is 1 photon in the cavity which put the system exactly in resonance. This technique, which consists in applying a field before and after in 2 different zones, is called the Ramsey interferometry. I don't want to enter into details, but you see here that what you get, you see that the atoms is found in one state. So you send atoms one after the other. You have these blue bars corresponding to atom in state 0. And then suddenly a sequence of atoms in state 1 appear, and then they disappear. And so you see the birth of a photon, which happens randomly. You see that many atoms see the same photon. So it's not a photoelectric effect, it's not a destructive effect. And then after some time, the photon disappears. So in this way, we define a quantum non-demolition photon counting process, which is quite different from the usual process. When you get a photon in your eye, the photon is destroyed by a photoelectric effect, and the photon is dead after. Here, the photon can be repeatedly measured, and you can do a lot of interesting memory storing and so on using this method. You can generalize that to a larger number of atoms. Suppose that you have prepared a field with 4 photons. You need more than 1 atom to detect them, because 1 bit of information will never allow you to distinguish between 0, 1, 2, and 3. At minimum, you need 3 atoms, because with 3 atoms, you can write a number up to 3 with 3 bits. If you have 7 photons, you need 8. If you want to go up to 7 photons, you need 3 atoms, and so on. And you see here what happens when you do this experiment. You see that, for example, here the field has collapsed to 4 photons, and then at some point, 1 photon is lost in the cavity walls. So you get to 3, 2, 1, 0 photon. And you see now what happens in quantum physics. The decay of the field is not a smooth curve as you expect classically. It goes by steps. If you do the experiment again, you will get other steps randomly. There is no way you can predict what kind of steps you will get. If you take an average over a large number of realizations, you get the smooth exponential decay of classical physics. I don't want to spend more time on that, but this experiment illustrates an ideal quantum measurement. The system, the measuring device here is a stream of 2-level atoms crossing the cavity, and you acquire information. Each atom provides you a bit of information until you collapse completely the system into a well-defined photon number. And all the postulates of quantum measurements are observed. For example, the fact that you have once you have detected 4 photons, you keep measuring the same number until the irreversible damping process occurs. And damping is due to the fact the system is not isolated as it should be for an ideal quantum system. So this is the last thing I would like to stress, is that you can also prepare Schrödinger cat states of the field in this way. A Schrödinger cat state is a state which contains many quanta, but which can be prepared in a superposition of 2 states which have different classical attributes. Here, what we are doing is that we start in the cavity with a coherent field, and this coherent field is represented in the complex plane by an arrow. The length of the arrow gives you the size of the field, and the direction of the arrow gives you the phase of the field. And according to quantum physics, the only quantum fact here is that the tip of the arrow is fuzzy, because you have the Heisenberg uncertainty relations. And then you send 1 atom across the cavity, and you prepare the atom in the superposition of state E and G. And it crosses the cavity. What happens when the atom crosses the cavity? The frequency of the atom is pulled, but reciprocally, the frequency of the field is also pulled. So the frequency of the field changes. This is a refractive index effect, which is classical, except that you have an index effect due to a single atom. And if the atom is in a superposition of 2 states, you have a refractive medium, which is in superposition of 2 different indices. In one state, the field will be pushed with 1 phase. In the other state, it will push with the opposite phase. And so what you get is a superposition of 2 fields pointing in opposite directions, which are entangled with the state of the atom. What you do next is that you mix again the 2 levels here, so that when you will finally detect the atom, you will be unable to tell whether the atom crossed the cavity in one state or in the other. And according to quantum physics and to the laws of entanglement, if you cannot say that, the atom is in a superposition of 2 states, is detected in a superposition of 2 states, and the field collapses in a superposition of the 2 states with opposite phases. And what you have prepared is a field which is at the same time with 1 phase and the other, which is what is called in quantum optics a Schrödinger cat state. So we detected these states here. I don't have time to enter into the details, but what we do, in fact, is once you have prepared the state, we send a long sequence of atoms, each providing enough information to reconstruct what is called the Wigner function of the system. The Wigner function is a map in the complex plane, which gives you the amplitude of the field for different complex amplitude. And you see here that what you get are two peaks here, which correspond to the two different phases of the field. And in between, you have fringes. These interference fringes are a signature of the fact that you have a quantum superposition of the two fields. So I like to show this. This is the live cat and this is a dead cat. And there is a quantum coherence between the live and the dead cat, which Schrödinger found ridiculous. When Schrödinger tells this story, it uses to illustrate the fact that there is something wrong, strange about quantum physics. But what is strange, of course, you never see that with a real large system, for one reason, that the time it takes for these fringes to vanish is inversely proportional to the number of photons. So here we did that with up to 10 photons. If you do that with 1 billion photons, which is what you have in the weakest laser beam, the time it would take for this to disappear would be infinitely short. What we did is to take snapshot of this function at increasing times, and we saw that these fringes very quickly disappear. And I cannot show it to you because I just realized that instead of presenting this myself, I let this on the computer, which is back in the room, and I have to act directly on the computer to show you the movie. So you would just trust me. This is that in a very short time, these fringes disappear, and we studied that this is a decoherence phenomenon. The decoherence rate is proportional to the photon number. And this is an illustration of the quantum to classical transition. Decoherence destroys the quantum coherence, and after a very short time, the cat is no longer dead and alive. It has to choose to be dead or alive. And here you see the two peaks remain because, in fact, this is a statistical measurement. Each time you do the experiment, you have to do it again. And the only thing you can measure is the probability to find the cat dead or alive in the end. I stop here just to tell you that this is a kind of studies which led to the Nobel Prize 2012. Dave Winand did the same kind of experiment with ions. And the physics is quite the same. And I think this is the reason why the prize was given in this way, because there was a kind of symmetry between what I did in Paris with my group and what Dave did with his group in Boulder. And I want to take this opportunity to really to emphasize the fact that this is not my work, it is the work of a team. I have been collaborating for many, many years with Jean-Michel Raymond and Michel Brune, who stayed with me over the years. They had been first my students and they remain in the group. The book which you alluded to was written with Jean-Michel Raymond, the book which describes these experiments. And since then, we have new young collaborators, Igor Dotsenko, Sébastien Glaise, and Christian Serrin, which are now working in the lab. And the second part, the last part of the talk, and it will be not too long, I will tell you about things that these people are doing now. The experiment I will be discussing now, I am not directly involved in them. I am retired now, I follow what the group is doing. And so I will be reporting about what they have been doing recently, which I find is very interesting. So let's look now what kind of quantum simulation you can make by controlling Rydberg interactions. I show you here two circular Rydberg states, which are at a given distance from each other in an electric field which defines the plane of the orbit. When you apply an electric field, the orbit is perpendicular to the direction of this electric field. What is the Hamiltonian which describes the interaction? Now it's no longer the coupling of an atom with a photon, it's the coupling between two atoms, and this is called the dipole-dipole coupling. It's proportional to the product of the two dipoles. This is a scalar isotropic part, and you have an anisotropic part, which is a product of the projection of the dipoles on the interatomic distance. This part has an angular dependence, which depends upon the angle between the direction of the electric field and the direction of which joins the two atoms. I will distinguish two different kinds of interaction. Suppose that you prepare the two atoms, one in the circular state n, the other one n-1. This state has, of course, the same energy as the state in which it is the first atom, which is n-1, and the second n. So again, you find the same situation I showed you before, but now with two atoms. And since these two states are coupled by this Hamiltonian, you have now a splitting, and this energy splitting is just a matrix element of this interaction. And you have an oscillatory exchange called a Forster resonance between this state and that state, which occurs with a coupling proportional to the inverse cube of the distance. Another type of interaction occurs when you prepare, for example, the two atoms in the NC, the same state. In that case, this state is not degenerate with anything else, because if you go upwards and downwards, it's not the same energy. So now it's a second order effect. And as I said in the beginning, it's an n to the 11th effect, and the interaction varies as 1 over R6. I will show you cases in which these two situations occur, but just here I summarize what we have to do that. You have to be able to excite the atom to Rydberg states, of course, from the ground state. You have to be able to keep them at a fixed distance from each other, because if the distance varies, you wash out the effect very quickly. You have to detect them selectively to distinguish between n and -1, and you have to be able to tune their interaction by applying electric and magnetic fields. Just to show you where we try to go, here, this is a lattice, an optical lattice in which you see 144 ground state atoms. How do you see these atoms? You see them because when you shine fluorescent light on them, they fluoresce. And so you see that you can arrange the atoms, and I will tell you more about that later, on a very regular array. And what happens then is that you can let the system evolve. If you apply a laser, you will excite them into Rydberg state, and you can let the system evolve between a ground state and a Rydberg state, or between two different Rydberg states if you apply microwaves. And you emulate in this way what you would have with spins on a lattice, because you can consider that if the atom is in the Rydberg state, it's like a spin up, and if it is in the other Rydberg state or in the ground state, it's a spin down. And you can manipulate the system to tailor any kind of spin-spin interaction between them. And you can realize an engineering interaction, which will be a product of Pauli matrices. A Pauli matrix is a 2x2 matrix, which tells you what happens on the spin. The sigma Z matrix has +1 and -1, like that. And a sigma X or sigma Y matrix is a matrix which has off-diagonal element, and which describe how the spin is switching from plus to minus when the atom interact. And the interaction can be tailored. You can fix the distance between the atoms, and the interaction is either 1 over R cubed or 1 over R to the 6th. This Hamiltonian described magnetism in quantum state matter physics, for instance. As soon as you have more than, let's say, 40 atoms, the size of the quantum space is 2 to the n and becomes huge, and no classical computer can really calculate, employing Schrödinger's equation, what's going on. So this system are simulating what happens in condensed matter physics. And I just make a little bit of advertisement. This is a picture taken from the work of Antoine Brouet at Institut d'Optique in Sacré. And here's a startup company which is now building the system which allow you to have this. So if you have the money, you can buy a system in which you have a lattice of ordered atoms, and I will tell you more about that. This system are also very interesting because you can find that the ground state of the system contain information which allows you to solve some optimization problems, like finding the best way to go between cities with losing a small amount of time, of the best way to distribute electricity on the grid. It explains why some private companies are interested in buying this from this kind of company. But I don't want to go into this too much into these details, and I just jump to this slide in which I tell you how do you excite these atoms. You use a stepwise process with two lasers which by a two-photon process, bring you from the ground state to a Rydberg state. And this is, as I said, a low angular momentum Rydberg state. And you see that if you vary the interaction time, you have a Rabi oscillation now between the ground and the excited state. And if you stop after half a Rabi oscillation, you bring all the atoms coherently from this to here. So there is a way with lasers to excite the atoms. The effective Rabi frequency is now the product of the two laser amplitudes divided by the tuning, so it's exactly the same thing as before. If you want to prepare circular Rydberg states, once you are here, you have a microwave pulse which brings you to another state, and then you apply circularly polarized radio frequency photons which bring you in the circular state. And it's a reversible process. Once you are here, you can de-circularize, and then with another pi over 2 pulse, de-excite and come back to the ground state. So you can do that coherently. And once the atom is back in the ground state, you can find out whether it is still here by using a method which is just fluorescence method. You apply a laser which brings the atom from here to the first resonance state, and you do it. This laser is bringing the atom back and forth, and it emits a lot of fluorescence photons, which tell you whether the atom is in the ground state. How do you keep the atom steady? You use what is called an optical tweezer. You focus the light very strongly, a non-resonant light, so the light produced by infrared laser, and you focus it at inside a cell containing cold atoms, magneto-optic. So the atoms are very slow, and at the focus, you have a force attracting the atom at the maximum intensity. It's called a tweezer, and the principle is very simple. This non-resonant atom is inducing a dipole on the atom. A dipole displaces electric and negative charges, and since you have a gradient of intensity, one charge is pulling stronger than the other one, and so you have a force which brings the atom here at the center of the trap. But you can, what happens that you can, so it's what you see. You see that when an atom falls into the trap, the amount of fluorescence that you detect with this counterpropagating beam is increased. You see, this is a trapping beam, and here you send counterpropagating a laser fluorescence which induce a laser which induces fluorescence, and you detect the fluorescence with this beam splitter which divert the fluorescence into this detector. When an atom falls into the trap, the level of fluorescence increases. Then a collision with a background gas empties the trap, and then the fluorescence light comes back. This has been done by many people, and starting at the beginning of the year 2000. An important point here is that if you have two atoms falling into the trap, under the effect of light, they collide, and they get too much energy, and they are ejected. So the only thing which may happen to keep the atoms there is either you have a single atom, or you have two atoms and you find zero, or if you have initially three atoms, two atoms are ejected and you are left with one. So it's an automatic way to get a single atom in the trap. But it's a non-deterministic source. What you can do is to have two atoms. What you do is you split your beam into two parts and you focus at a slight angle. And now you have two focal points, and you have two atoms at a well-defined distance from each other. And here, a very interesting phenomenon occurred, which is called the Rydberg blockade. How does it work? You start by having two ground state atoms, and you want to excite them with light. So first, what happens that you excite one atom from G to the Rydberg state. That's simple. But if the atoms are too close to each other, the two atoms are shifted by the dipole-dipole interaction. And you see now that the laser which excited the first atom is unable to excite the second. This is called the dipole blockade effect. One atom excited blocks and prevents other atoms in the vicinity to be excited. This blockade effect is very interesting, and this effect which triggered the interest into these studies. And I just want to show you why by going on. So I don't know why it does not work anymore. Yes, this blockade produced entanglement, because the light beam which excites the two atoms has a waist which is much bigger than the distance between the atoms. So in fact, what you excite is a symmetric superposition of an atom excited with the other in the ground state. This is an entangled state. So you see that the blockade effect prepares automatically entangled states of the two atoms. And so in fact, what you realize is a quantum gate just by taking the blockade effect into account. Another important point is that the oscillation, the Rabi oscillation between the ground state and this collective state, this entangled state, is no longer omega, but it's omega square root of 2. It's easy to understand that because of the square root of 2 that you have here. And you can generalize that to a collection of atoms. It accepts to work. Yeah, you see that if you have many atoms within a Rydberg blockade radius, the laser will be able only to excite one of them. And in fact, it will excite a symmetric superposition of all the atoms. And the coupling is now omega square root of n. This has been observed in experiments, and this blockade effect is, as we will see shortly, very interesting. And it has been theoretically studied by the group of Peter Zoller, Lukin at Harvard, and so on. I show you here very briefly an interesting experiment which was performed by Emmanuel Bloch in Garching. He has prepared a lattice of ground state atoms and then send a laser to excite them into a Rydberg state. And the blockade radius is about half the size of the sample. So it means that you can only excite atoms if they are as far as they can be into this superposition. In this case, you can excite a pentagon of Rydberg atoms. How do you see that? What you do is that you excite, and then you send a laser which sweeps away the ground state atoms. And then you bring the atoms down by the opposite process, and you find the atoms which were in the Rydberg state, which come back. And you see this picture, the kind of picture that you see. You see 5 atoms. If you do the experiment again, you will find another disposition of 5 atoms or another one, because of course you don't know in which directions they will come. And you can stack all these pictures by putting them with the same axis. And then you get a picture like that. So it's not perfect, but it's a rather interesting picture. The theory gives you that, so it's still imperfect, but what you can call this a quantum crystal. Because in fact, what laser excitation prepares a superposition of all the possible configurations. And when you detect, you collapse into one of these possible cases, and you reconstruct everything by doing the experiment again and again. So this was done with an optical lattice obtained by intersecting laser beams. So the distance between the atoms was only 1 micron. And it was a tour de force to be able to resolve optically with an optical microscope points which are 1 micron apart because of the fact that you cannot have a resolution bigger than the wavelengths. So all these experiments have become much, much more interesting and easier when you have replaced this kind of lattice by a tweezer lattice produced by a holographic method. And I would like to say a few words about that. Use what is called a spatial light modulator for holography. This is a plate with pixels. Each pixel is a liquid crystal which has a refractive index that you can control electronically. And so you can change the index on each of these pixels. And when you send light on this system, what you get is you can modulate the phase of the light across the plane. And now you use the properties of very simple optical properties telling you that the focusing gives you the Fourier transform of the phase distribution that you have initially. So if you want to have any kind of intensity distribution here, you can calculate the phase distributions that you need to get after Fourier transform what you want. And this is the method which has been pioneered by many people, including by the group of Antoine Bourweis. It's the same kind of setup. You have this spatial light modulator, you send the laser light, you focus, you get here your distribution of tweezers, and you imprint that on a cold ensemble of cold atoms. Some atoms falls in the trap, and you send fluorescent light to produce the fluorescence, and this is what you get. You get something like that. Of course, you have holes because 50% of the time you don't have any atom in the trap. But what you can do is that you can use a tweezer to take atoms on the periphery and put them in the holes using a computerized process. So it's a kind of Maxwell demon, which decreases the entropy of the system by preparing the regular array of atoms that I told you before. And so these are kind of experiments which are done by Antoine Brouwer, by Michal Lukin. You see what happens when you excite the atom close enough so that the Rydberg blockade take effect. The atoms, when you detect the system by bringing the atom down to the ground state, no, you don't bring the atom down. What you do, you prepare your system, and then you look at the fluorescence. So only the atoms which are in the ground state fluoresce, and you have here places which seem empty, but in fact they are not empty. They are with Rydberg atoms. And so the Rydberg atoms arrange themselves so that you have one Rydberg atom surrounded by ground state atoms. This is an antiferromagnetic phase, exactly what happens in real solid state matter when spins tend to align along opposite direction. So a lot of very interesting condensed matter physics is being done with the system. Last point I would like to end. This is what the Pascal startup can sell you. The problems that you have here is that the circular Rydberg atoms are not trapped. Once the atom is prepared into a state, circular state or not, it is no longer sensitive to the focusing of to the tweezer in the ground state. In fact, it's quite the opposite which happens, because the Rydberg electron is almost free. So what the laser field does is to force the oscillation, and it gives an extra energy to the electron. It's called the ponderomotive force. And so instead of having a potential well, you have a hill. And the Rydberg atom is rolling out of this hill and escaping very fast. So after a very short time, you lose completely the structure of the atom in the excited state. If you want to avoid that, what you have to do is to replace the tweezer traps by what is called a hollow trap, or it's called a bottle beam trap. It's a configuration of light which surrounds each point by light all around. So the atom, instead of being at a maximum of electric field, is at a minimum, and he cannot escape. And so all the game is now to switch from a tweezer to a bottle beam trap when you excite the atoms. And show you here briefly. Now, the setup, you have two spatial light modulators, one which is producing the ground state tweezers, and one which is producing the Rydberg atom bottle beam trap, and the same detection procedure and so on. And so you have to switch from one system to the other. And you see here what the group in Paris did and what they are doing now. They have now 18 traps, 6x3 tweezer and bob arrays. You start by the tweezers, you trap the atoms in the ground state. Then suddenly you switch off the tweezer and you excite quickly by laser excitation into Rydberg state. Once they are in the Rydberg state, before they have time to fly, you switch on the bottle beam. So the atoms are trapped, and you use microwave and radio frequency to circularize the orbit. So you have circular atoms in the traps, and you let them evolve and do physics. That's the interesting part. And then you do the inverse procedure. You decircularize by microwave pulse. You de-excite by the laser pulse, double laser pulse. And then you switch the tweezer back again, and you probe to find where the atoms are. If the atom stayed at the same level, you will find them at the end. If the atom went into another level, they will be lost, and you will see them as a whole in the final picture. So I just go fast, and I've explained that, and this is what you can see. What they have done then is to induce microwave Rabi oscillation on a transition between the level 52 and the level 50. And they do it on the 18 traps, and they look at the Rabi oscillation. And you see that now you can distinguish the Rabi oscillation of each atom in each trap, independently of the other. And the population in the initial state is measured optically when the atom come back, because if they go to the other state, you don't see them. And you see that the Rabi oscillation is slightly different because you have inhomogeneities of the microwave field, which does not give exactly the same amplitude. But you can also measure by field ionization And then it's not selective, it's not state selective. What you see is an average of all these oscillations, which show collapse and revival, because you have slight difference in frequencies in the different traps. And so by analyzing this, you can analyze the inhomogeneity, the imperfections in the system. This experiment is done with a distance between the atoms so large that you have no interaction. So it's a pure one-by-one, each atom interacting only with the microwave, not with the others. Then we decrease the distance between the atom, and we start to see the phenomenon that we really want to study, and I will use a couple of minutes to tell you what we can see. For instance, look at the dipole-dipole interaction between two states, circular state 51 and 52. It takes this form. You see, it has an angular dependence, which is due to the angular part of the interaction, the famous 3 cosine square theta minus 1 term, which means that there is a magic angle for which the dipole-dipole interaction vanishes. Below this angle, you have an interaction which has one sign. Above this angle, it has another sign. And this angle is just the angle between the perpendicular to the plane orbit and the vector which joins the two states. So you can vary this. How do you vary it? You vary it by modifying the direction of the electric field which decides the plane of the orbit. So you can study that by microspectroscopy. This is the energy level of the two states of the system where the two states are in the state 52. Here you have the two states in state 51. So this is plus plus, and this is a minus minus spin system. And you see that here in between you have the state in which only one atom is excited and not the other. But I think now we start to understand what happens, because these two states are coupled. You get the splitting, and the splitting here is just a matrix element of this thing. How do you see that? You just look at the microwave spectrum. What is the probability to go from 52 to 51? You can go either by two photon transition like that, or by a photon transition going to the plus state here. You cannot couple to the minus state because the two amplitudes interfere destructively. So you see, you expect to see two lines. And indeed, you see two lines. One line corresponds to is a line going to from here to here, and the other line is a two-photon line here. And you see that this is for 0 degree, theta equals 0 degree, this is for theta equals 90 degree. You see that the interaction change sign, depending upon this anisotropic term. And you see that if you choose the magic angle, you have only one line, so you can cancel the interaction. So you can really control everything in this way. We did the experiment. They did the experiment by changing the angle, and you see the cosine square minus 1, and the value for which you cancel the interaction here. And you see also in semi-logarithmic scale how the interaction decreases as 1 over d cube. So everything seems to be under control. The last, now I ask you just 1 minute of patience before I finish. I want to show you how the dipole blockade effect can be used effectively. This is a microwave experiment which explores the spectrum, but what we really wanted to see is the dynamical exchange. If you prepare 52, 51, if you start from one state, it will oscillate to the other state. They will exchange their energy. But for that, you have to prepare one atom in one state and the other atom in the other state to start from this state, which is not an eigenstate and which will evolve as a superposition. But it's very difficult to do with lasers because the laser waste covers everything, and you can only excite all the atoms, the two atoms in the same state. So what they did is to use the blockade effect in a very clever way. The atoms between which you want to see the interaction are the atom A and B. And here you have an ancilla atom, C, which is used to block selectively the interaction of the atoms between themselves. So you start by a configuration which corresponds to the magic angle. So atom A and B don't interact with each other. On the other hand, atom A interacts strongly with atom C because of the dipole blockade effect. And then you start by exciting the two atoms in 52. And then what you do is that you apply a microwave, which will bring 52 to 51 without touching this atom, because this atom is inhibited by the dipole blockade effect. And so once you have done that, you have one atom in 51 here, one atom in 52 here. At this point, you change the angle of the electric field to block this interaction, but to let these two atoms interact with each other. So this is just summarized by these things. And what you see now, when you detect, you see the oscillation in a phase opposition between this state and this state. So you can induce this oscillation. And of course, the frequency that you find here is the same as the frequency which was measured before by the microwave method. So this is what they are doing now. This is not published, and this is the thesis of the last students they have in the group. I just want to say a few words to conclude. First of all, I think I convinced you that circular Bohr atoms have gone a long way since they appeared in theoretical physics in 1913. From ideal theoretical concepts, they have become experimental objects which can be manipulated, observed individually. Their coupling to photons or between each other can be controlled with great precision. While they played initially an essential role to introduce quantum concept into the description of atoms, they give us today an opportunity to explore the complexity of quantum physics in many-body systems, which all these experiments are heading to. This blue sky research is often presented as a step towards the building of the mythical quantum computer. I want to emphasize we are very, very far away from this quantum computer, because there is a lot of noise in the system, there is a lot of imperfections, decoherence plays a role, and so on and so forth. But even if you don't get to the quantum computer, there is a lot of very interesting things, a very interesting experiment happen. What is sure is that this physics is fascinating and promises many surprises in the future. And thank you, and I apologize for having been too long. Thank you.
Thank you very much for the excellent talk. As usual, you give us the opportunity to listen from the beginning to the end. I mean, you are telling us what is being done now, and that is very important, and we appreciate your generosity.
Thank you.
Thank you. And then, Alejandro?
Happy birthday. Oh, thank you.
I guess I can only ask one question, but I have a sort of a superposition question. The first one you hinted at is what you think about quantum computers and all the news about it. But my question is about the fundamentals of quantum mechanics, and what is your view of this non-local or DCPR phenomena that we don't really know what's going on? That's my superposition question. Thank you.
Oh. Okay, it's a very deep question. People have been discussing interpretation of quantum physics for at least 100 years. And there are two schools, as you know. There are people who say, shut up and calculate, and the other school. In fact, at the end of the 1920s, beginning of the 1930s, there are two famous books which have been written about the principle of quantum physics. One was a Dirac book, in which he does not say a word about all these problems. And the other one is the von Neumann book, Mathematical Foundation, in which he gives a lot of attention to this problem. In fact, von Neumann discusses the idea of hidden variables much before the EPR experiment, and he says that hidden variables would destroy all the consistency of quantum physics, that there cannot be hidden variables. So before Bell's inequality, he had this intuition. People say that his explanation and his demonstration of that was faulty, but in fact, he was right. Dirac, when Dirac was asked question about that, he said, there are a lot of people who talk about interpretation of quantum physics. I am not interested in that. I am interested in much more important issues. So I can use some, I can, it's clear that nature obeys to this kind of thing. It's clear that you have randomness in quantum physics, that you have non-locality. And but it's clear also that there are things that we don't understand yet, that there is no a consistent theory of general relativity and quantum physics. So some people believe that the day we'll have a consistent theory, some of this problem will disappear. But this is, for the time being, just very fuzzy. I think it reminds me what happened at the beginning of the stories that I told you, when people were asking questions about the ether, and then Einstein came and says there is no ether. And so maybe one day we'll find that this problem don't exist. But of course, it's not an answer.
Please, feel free
Yes.
to ask anything. Yes, Ricardo.
In the last set of experiments, suddenly you have many atoms and they are spread in space.
Yes.
So now could you also start mapping the spatial distribution of the modes, not just the photon numbers? And which richness do you get out of these experiments?
Excuse me, mapping what?
Like the spatial distribution of the modes, since now your atoms are localized in different points, they oscillate at different Rabi frequencies and so on.
In fact, this is an imperfection, because what we would like to have is to have the same excitation for all the atoms. So in fact, the system has a few tens of micron, maybe 50 or 100 micron, and over this distance, which is many microwave wavelengths, you have, the amplitude is not constant. So you have, but we could improve on that. We could decrease this. And in fact, we will have to do that. I did not have time also to discuss other ways to improve. We have to decrease the temperature, because for the time being it's at room temperature, which makes a lot of black body radiation induced transition. We have to work at very low temperatures, and we can even suppress the remaining spontaneous emission by having the atom, all this sample of atom between two plates whose distance is smaller than half wavelengths. Then spontaneous emission is completely inhibited. So you have, in principle, you have a very long time. You could look at the atom for many seconds, which would correspond to many thousands of oscillations, and look at quantum effects and the buildup of quantum correlations at a very long time scale with an Hamiltonian that you can control. So this is a dream of what they hope to achieve. Yes.
Yes, there is one question. Well,
to me that you're a little bit skeptical about a quantum computer.
Not a little bit.
Okay. But anyway, I mean, I'm curious to know whether a Rydberg quantum computer would have an advantage over other proposals.
I don't know. First of all, I want to say, I was joking. What I want to say, I am not skeptical about the quantum computer. I am very opposed to the overselling that people are doing, claiming that they have a better system than another one. And I will never claim that this Rydberg system is better, for example, that superconducting circuits using Josephson effect and so on. The problem is that what I have shown you here is some qualitative results. We observe these effects, but if you want to build a computer, you need to have a fidelity of 99.99% on each of these operations. And we are very far from that. And you have to be able to fight decoherence, which I show you with the Schrödinger cat issue. In fact, what this computer would do is to be a kind of super Schrödinger cat with billions of bits computing in parallel without errors or with controllable errors. So I don't know if it will happen, but I'm sure that very interesting physics will happen in the meantime, and maybe some surprises. And what I want also to emphasize that these people, Einstein, Schrödinger, Bohr, they never claimed that they will build a GPS system or that they will build lasers. They did not even know that it happened. And they never said that they were making a revolution. And now everyone who has a small experimental setup in his lab says that he is at the tip of a second quantum revolution. And this is what I don't like. And maybe I'm overreacting against this trend. I don't like also the fact that if you want to do an experiment like that, in the proposal, you have to say that you're on the way of building a quantum computer. I don't think it's necessary.
And in the middle there, I don't know.
Thank you. You talked about specifically a kind of trapped atoms and Rydberg states of it.
Yeah.
And in the conclusions, you talked about the applications that it could have in quantum computing.
Yeah.
There are kinds of qubits called like this, the
Yeah.
trapped ions qubits.
Yes, yes.
What are the role that plays the Rydberg states in this kind of qubits? And second hand, I didn't know it was your birthday. It was your birthday today, but I brought some kind of gift. So
Oh,
if
okay,
I
thank
could give it to you, it would be awesome. No sé
Thank
si
you.
alguien me puede apoyar pasando el.
Oh, thank you very much.
No,
And this gives me the opportunity to add something. I did not acknowledge all the group. In fact, I want just to emphasize the fact that many groups worldwide are working with Rydberg atoms today, and all this was initiated by the proposal by Peter Zoller, Misha Lukin, Buretic in Innsbruck, and at MIT and Harvard. The Institute d'Optique in Paris with Grangier and Bowes has made very great progress. Bowes has created a startup, Pascal, and it's not a joke that you can buy the holographic system which allows you to prepare these arrays of atoms. We did not use them. We did, the group in Paris did that independently because we want to prepare circular states. And in the case of Bowes, for the time being, they work on low angular momentum states, which are much shorter time lived. There is a group of Garching in Germany, and University of Wisconsin, Strasbourg University, many others. And here you have the Paris group with a lot of the people I mentioned at the beginning, and a lot of very dedicated graduate students who do things which amaze me, because each of these experiments is a tour de force, experimentally speaking. And I would have been personally absolutely unable to do it. The ways that students are now asked to control lasers, computers, cryogenics, vacuum techniques, and so on, is absolutely unbelievable. And I want to really recognize that today.
Yes. Any other questions? There, just the last two ones, I think. Mm-hmm.
Merci. Bon, je ne parle pas l'anglais. Bon, si vous n'avez pas de problème, je peux parler en français.
Okay, Carlos.
Oui.
As you want. No, you can speak English.
Oui, croyez-vous qu'il y a ou qu'il y aura une autre révolution quantique, c'est-à-dire on va rappeler la mécanique et la mécanique classique de Newton, par exemple, et la mécanique de Lagrange, et maintenant il y a la mécanique quantique. Bon, vous croyez que
No.
il y aura à l'avenir une autre révolution mécanique?
Okay, it's very hard to tell that there will be no revolution. It's very hard to say the opposite. But I strongly believe that the quantum concept, the idea of state superposition, of non-deterministic behavior of the laws of nature will stay. And how this will be reconciled with general relativity, which is in the frame of stated in the frame of classical physics, remains a mystery. I don't know. And it raises cosmological questions that I don't, I'm not a specialist about. So my own feeling is that quantum physics will not come back to Newton. I don't want to say that Newton was wrong. Newton was Newton mechanics has been applied for centuries to predict the motion of planets, the perihelion of Mercury, and the existence of Neptune by the perturbation to Uranus orbit. So this is a solid physics, but it doesn't apply under the condition of relativity or in microscopic systems. So each stage is not destroying the previous one, it's just building up on knowledge. And maybe something with a theory which will correct in some way quantum mechanics will appear, but it's very difficult. So what I think is fantastic about quantum physics is that it's a kind of consistent system. Each time you want to add something, to modify slightly in order to become more in accordance with your intuition, you find that the whole system will collapse. A very famous physicist like Steven Weinberg has tried to add some kind of non-linearity into quantum physics, and then he gave up and he said, it's not possible. If you do that, everything will fall down. So I don't know. What I do, what I have done all my life is to do experiments and trying to understand things through experiments. So I cannot answer about big conceptual revolutions, but my feeling is that there is something deeply true in quantum physics. Yeah.
Okay, and the last question, the last.
I know you mentioned I know you mentioned in the end how it's still highly debated whether it's possible to make a quantum computer be using a Rydberg atoms or not. I was wondering whether there would be any other areas in condensed matter or physics in general where this model of Rydberg atoms could be applied.
I think it's applied in all systems which you can describe by two-level system interacting on a large scale with each other. The Ising model, the magnetism, some topological models in which you place atoms in some defined positions. And I don't know enough about condensed matter physics myself to enter into the details of this physics. It's just the beginning. And whether one will find new phases. In fact, some people believe that it can be a way to find high TC superconductivity, that you can arrange atoms into configuration which will raise the critical temperature for superconductivity, but it's still open. And the problem is that what you can do with the system is to emulate situations that you cannot solve exactly with a classical computer. And this is interesting by itself. And what makes things more easier than the computer is that for many problems, even you can accept some level of noise, because what happens in condensed matter physics, you always have some noise. So you can accept some level of noise that you couldn't accept if you want to build a full-fledged quantum computer.
Okay.
Thanks.
So let us think again.
Okay, thank you. Thank you very much.
La salida será por la puerta izquierda.
I just want to add one thing. Today was my birthday. Next week, as you have seen in the first slide, I'm going to Stony Brook to give this lecture. I think I will try to do it a little bit shorter for them, but this will be the birthday on 19th of September. It will be the birthday of my wife, Claudine. So.
Dr. Haroche, this is how we celebrate birthdays in Mexico. So please join us in singing las mañanitas to Dr. Haroche today.
Thank you.
No se oye.
Thank you so much. It will be a memorable birthday for me. Thank you very much. We remember this day.